So, good morning. Let's start, this time for real. Okay, good. So, last time we started looking into chosen plaintext security as our next security model for encryption schemes. Today, we'll see how we construct secure encryption schemes, secure in the sense of chosen plaintext security. The construction based on pseudonym functions in this form is, although not really practical, the way we do that is extremely important because this is the construction, or this type of construction underlies all practical constructions with different primitives, but this is really what we do in modern cryptography, and I will explain this in more detail when we come to the construction. But then at the end, I will argue that this chosen plaintext security is still not good enough. We need something else, namely chosen ciphertext security, but this is an important first step towards that, and chosen plaintext secure encryption schemes are a building block to achieve then the ultimate goal of chosen ciphertext secure encryption schemes. Okay, let's briefly look at the chosen plaintext indistinguishability game and the security notion that's based on this. Again, we have an adversary and a challenger. Again, we have this encryption scheme pi. The challenger first chooses a key, then, and that's the difference to eavesdropping, the adversary can ask for the encryptions of adaptively chosen messages of his choice. Adaptively, so given the answer to the first query, he can pick the second one, and so on. And after having seen these encryptions of the plaintext of his choice, he outputs two messages, M0 and M1, which again have the same length that as before. As in eavesdropping, we cannot hide the length of messages given an encryption. That's typically impossible. Then the challenger chooses one of the two messages, encrypts the message, and sends that ciphertext to the adversary. The adversary can ask for more encryptions here and eventually has to output this bit B prime that is a guess for the bit B that the challenger chose. So the indistinguishability part here is the same as in eavesdropping, but we give the adversary more power in the sense of he can ask for these encryptions of his choice. Note that he cannot compute the encryptions himself because these encryptions are done with a chosen key here, which is not given to the adversary. So he does not have the knowledge required to compute these encryptions himself because he doesn't know the key. And then we had our usual visualization of this, and we can then define indistinguishable encryptions under chosen plaintext attacks or CPA security as for every probabilistic polynomial time adversary, there's a negligible function such that the CPA advantage defined as the difference of the probability of outputting 1 in the game and 1/2 is negligible. Okay, and again, as before, as usual, we restrict ourselves to probabilistic polynomial time adversaries, and we allow here this negligible difference. But basically it says you cannot do better than guessing, because 1/2 is the probability of just doing a random guess. You allow a little bit better, adversaries to be a little bit better, but not much, namely only negligibly better. Also notice that because we have a probabilistic polynomial time algorithm here, the number of queries that the adversary can ask is polynomially bounded, because every query encryption he has to provide that encryption, the plaintext, right? He has to send that thing to the adversary, so he can only do that polynomially often. And one important observation here is that a CPA secure encryption scheme cannot have a deterministic encryption algorithm, because then you could just ask for the encryptions of M0, M1, or just one of the two, and then you would know which of the two messages was encrypted by the challenger. Okay. And then we can generate this to multiple messages, the multiple message indistinguishability game. Recall that for eavesdropping security, we could not prove, in fact, it's not true, that if you are eavesdropping secure or if you have indistinguishable encryptions against eavesdropping attacks, that you have actually indistinguishable multiple encryptions against eavesdropping attacks. Right? And the multiple indistinguishability game, multiple messages in the indistinguishability game is required that the adversary outputs two vectors of messages, and then these one of the vectors is encrypted. Right? And then he has to decide which of the two messages is encrypted. This models, among other things, the electronic codebook mode, which I will talk about later today. So this is the straightforward multiple message indistinguishability game. We can define the security as before, usually. But then we have the important theorem here that for CPA securities, CPA security or CPA security already implies that we have also indistinguishable multiple encryptions. A very strong hint that this is getting towards a useful, good definition of security, because at least you always want to be able to use an encryption scheme with the same key several times. In eavesdropping, that was not guaranteed to yield something that's secure. Here it is. In CPA security, it is guaranteed to be secure. As I said last time, I will prove this theorem, or variant of this theorem, in a later lecture. In a slightly different context, namely public key encryption schemes, but the proof is more or less the same. Okay. And then I will later on go to ECB mode. That's something that we'll skip here. Now, now we want to go to the construction of CPA secure encryption schemes from general assumptions. And remember, in the eavesdropping case, we used pseudorandom generators to construct eavesdropping secure encryption schemes. Here we'll need something that's stronger, something that has more structure, that we can exploit in a more refined way. And the way what we will use are so-called pseudo-random functions. And we already talked last time about random functions, functions where we pick an element uniformly at random simply from the set of all functions with a specific domain and range. And for our purposes, the important setting is where domain and range are both 0, 1 to the n. Okay? And then we saw that the number of functions in this set is denoted by func n is 2 to the n times 2 to the n. We can also view this a function from the set as simply specifying for each input, for each argument, an image. Since there are 2 to the n arguments, possible arguments, each image is defined by an n-bit string, and we can combine them in any way. This is really 2 to the n times 2 to the n. That's one way of viewing it. But the point is that if we give n, then in time polynomial in n, you cannot look at the whole function, because that has exponential length in n. Okay? That will force us to use a different model of providing an adversary with a function, okay? Because we cannot specify it by giving it all possible images, the complete description. So as I said, we call a function generated by picking a function uniformly at random from the set a random function on n bits. Okay? This here is not necessarily this is not doable in time polynomial in n, because we needed to pick n times 2 to the n bits uniformly at random, but never mind. We won't be able to do that, actually, or won't be forced to do that. We looked at a few properties of random functions. Namely, what we can see is that if we have s different arguments and s possible images, the probability over picking a function uniformly at random from the set that we have these relations f of xi is equal to yi for each I is exactly 1 over 2 times 2 to the n to the s. So it's 1 over 2 to the n times 1 over 2 to the n times 1 over 2 to the n s times. And from that, we have this conditional probability that if we already know t function values for a random function, then the probability that at a new point we have a specific value over the choice of the random function is 1 over 2 to the n. Which means that we can always think of a random function as providing for each argument a new image by picking that image uniformly at random, independent of what we have done before. Just making sure that if we have already fixed an image, we have to keep that, right? Because otherwise we don't get a function. But other than that, it's like, you have to, as a challenger, you have to provide a new image, say, pick one uniformly at random, send it over. And that way we can actually sort of specify function efficiently, namely if we only have to provide polynomially many images, we can just pick those images uniformly at random and independently. Okay, so that's where we were last time, basically. So once we have random functions, we will define pseudorandom functions as functions that, although they are not random, they look like random functions to probabilistic polynomial time adversaries. That's always what we do. If we have something, a random object, then we can also define a pseudorandom object by simply saying this is something that cannot be distinguished by a probabilistic polynomial time algorithm from the random objects. That's our definition of pseudorandomness. Okay. Here we need a few more technical things before. These are really technical, makes life easier, simpler. We just need to fix some things. But the pseudorandomness that comes later is the important part. So first of all, we look at keyed functions. So a two-input function, f, which takes sort of two bit strings from 0, 1 star and outputs an element from 0, 1 star, that's called a keyed function. Okay? So it takes always two inputs, k and x. Okay? And the first input we usually call the key and denote it by k. Okay? And we call f efficient if there is a polynomial time algorithm that on input k and x computes the image. Polynomial time means it must be polynomial in the length of k and x, the combined length of k and x. And usually what we do is we write the first input, the key, as a subscript. So instead of, and denote then, and then look at restrictions of the function. So if we fix the key to a specific value k, and then only look at the value, the thing where we actually exploit, fix this k, and then only have a function from 0, 1 star to 0, 1 star that we denote by fk. So fixing the first coordinate, we get a function, or the first input, we get a function from 0, 1 star to 0, 1 star. We call that fk of x. It's defined like this. Okay. So often you can also think of such a keyed function as a family of functions. You can think of f as all these things here, k and 0, 1 star. But we will even restrict that further. Okay. Now let's look at the setting that we usually use. Usually we can associate three functions with such a keyed function f that's called L key, L in, L out. And in our setting where we talk about cryptography, there's, as I said, usually a security parameter, 1 to the n, and that security parameter determines the key length, the input length, and the output length. So we want that this fixes certain parameters. Okay? And then once we have that, then a key k is chosen usually by picking it from the set of all keys of this length. Okay? And then we consider the restriction of fk to the domain consisting only of those inputs of length L in of n. Yeah.
One question, how exactly do we choose the key k?
Picking it uniformly at random from the set. This is our notation for picking an element uniformly and random from.
Yes, but how do we pick it uniformly at random from the set?
Pick L key of n many bits uniformly, independently at random.
With a random generator then?
We assume, that was one of the things that I said at the very beginning, we assume that we can pick bits uniformly at random.
Okay.
Yeah. It's difficult in practice, actually. Yeah?
Are L key and L in the same length, or they could be different?
In the general setting, they can be different. I will say something later, in a second, about these things, because I want things to be much easier. Okay? So then we can restrict this function, fk, which is defined from 0, 1 star to 0, 1 star. We can define it to this domain. This is usually the thing. And we assume that then for all things of this length, the output has L out length of n. So that if you have a fixed input length, we assume that the output length is also the same all the time. Okay? Too many parameters. We usually assume that all these things are n, just for simplicity. In practice, that's not necessarily true, if you do, but it's really much easier, and it's really without loss of generality. So if we have the security parameter n, we have the key length n, we have fix the input length to be n, and we assume that the function is what we call length preserving. So if we, for all k's of length n, if we provide fk with an input of length n, the image is also of length n. Okay? So, and then what I usually do is I usually talk about then, so if we have a key, if the key is in 0, 1, 1, n, then we really look at such a function, right? Everything's n. And that's really what I usually mean when I talk about fk. I restrict everything to this domain 0, 1, n. I'm not really interested in 0, 1 star at that point. Okay, and that's called a length preserving function. And often when we talk about this thing, this function here, often it's not really defined for 0, 1 star, 0, 1 star, but it's really, if the first parameter of length n, I'm only interested in all things that are of length n. And it's not even defined on the other things. I don't care. I'm really just interested in this part. And if it's outside that domain, it's not defined, who cares? Okay. Yeah? Let's maybe look at an example. here is a function that I'm going to use later on. I really define fk only, so for all. We set fk to be, it is length preserving. And what it does, it maps x, which is x1 up to xn, to y1 up to yn, where yi is defined to be xi times ki xor xi plus 1 times ki plus 1. And that is done for I from 1 to n minus 1. And yn is defined to be xn times kn xor x1 times k1. So what I do here is, so this is really just multiplying. So 0 times 0 is 0, 0 times 1 is 0, 0, 1 times 0 is 0, 1 times 1 is 1, and that is XOR. So I go through position by position, multiply the corresponding positions in x and k, and then k of x, which is y1, y2, and y1 is k1 times x1 is 1, x or 0 times 1 is 0, so that's 1. And you know, here we have the cyclic shift is actually the same thing. So y2 is this and this is 0, x or this times this, because I do the cyclic shift, so this is 1. Just do the multiplication. In this case, you can easily convince yourself that y1 is always equal to y2. Right? So just do the cyclic shift immediately. So the first element and the second element are the same. Yeah. I'll come back to this function later. Okay. Now, I said a pseudo-random function is one that cannot be distinguished by polynomial time adversaries from a random function. How do we give the adversary access to the function? In the pseudo-random generator case, where we had a pseudo-random versus random string, it was easy because the adversary just got a string of a certain length, and then he did something on that. Notice here that, as I said, we cannot give, in the pseudo-random function definition, the access to a function cannot be by providing it with all possible images for all arguments, because that would yield a string that's exponentially large. It doesn't make sense to give a polynomial time algorithm something that's exponentially large, or we don't want that. Okay? We want to just give it sort of snapshots of the function. You can look at this function value, you can look at this function value, you can look at this function value, and so on. And we do that by giving it oracle access, as we call it, to the function. So the adversary is not given access by giving it a complete description of the function, but just providing it with specific argument image pairs. But those can be chosen by the adversary. So this is similar to the thing that we did actually in the definition of plaintext indistinguishable encryptions. And we call that oracle access. So we say that an algorithm D has oracle access to a function U to R if it can write X from U into special memory salts, go to a special state, call this query state, and then it gets in one step the function value. Okay? So writing these things into the salts takes time, at least as long as the X is, or the description of X, but then it gets the function value in one shot. So this is like also what we did in the chosen plaintext game already, right? So although they are oracle access to the encryption function, right? This can be realized in the same way. Okay? And we have a special notation for that. We write this D superscript F to denote that an algorithm has oracle access to a function F. Yeah? And now our definition of pseudorandom function will be very similar to the definition of a pseudorandom generator. You get access to, in the pseudorandom generator case, you got access to a string. And then we said, in the pseudorandom generator case, just the whole string. You got the whole string. And then an adversary should behave almost the same whether the string was chosen uniformly at random from everything or by picking it pseudorandomly, namely picking an S and then applying the pseudorandom generator on it. So our definition of pseudorandom function is very similar, except that the way we provide access to the input is different, or to the function. So, and so we restrict ourselves to a keyed, efficient, and length-preserving function. So it's a two-input function. We can evaluate it efficiently, and it's length-preserving, so keys, input, and output lengths are all the same, n. Okay? And F is called a pseudorandom function, a PRF, if for every probabilistic polynomial time algorithm there's a negligible function mu. You know this. Now we look at difference between two probabilities. So D gets 1 to the n, and either it gets access to fk of x, function fk, where k is picked uniformly at random. Okay. And then we look at the probability over the choices internally to D, the choice of k, that it outputs 1. And here it gets access to a truly random function. Yeah? And then we look at the probability that it outputs 1. Okay? Okay. But the D just works with functions for which it has oracle access. And we'll look at this example in a second so that hopefully that may make it clearer. So again, we'll look at what's the probability that it outputs 1 if it gets access to a function picked in this way and in this way. Okay? And this difference here we call the distinguishing advantage of D. Okay. I want to make this definition a little bit clearer. We'll look at this example here and show that this is not pseudorandom. Again, I won't be able to give you examples of pseudorandom functions because those are quite hard to construct. At some point I will probably tell you a little bit about it, but giving specific examples is not so easy. But we'll see that this guy here is not pseudorandom. And what do we have to do to show that this function that I defined over there is not pseudorandom? Well, we have to define a distinguisher, a function d, for which this advantage is non-negligible. Right? Okay. Okay. Can I erase the definition of the function? Do you have that in mind, or maybe I just leave it here a little bit and then work around it. This should be enough. So any ideas how we can define a distinguisher that behaves very differently if it gets a function of this type with k chosen uniformly at random over all bit strings of length n, and it gets a truly random function, again from n bits to n bits. So we need to define a distinguisher that just gets oracle access to a function. Right? It knows n, and it gets oracle access. And then we define this for any function, and then we have to analyze these two probabilities and argue that they are, for this example, and given this distinguisher, they are very different. They are different. They differ by something that's not negligible. Yeah.
And maybe we can XOR all the epsilons of all the y's, and in the end the keys should cancel out, and maybe the x's as well. So we have only one value, which is, I guess, 1.
But where do you get the y's from? Y's are the y. By y I denoted the image of x. Where do you get the y's from?
Here we have to call the function, right?
Yeah. Okay. So you want to query function, query f on some input.
Some n which is of even length, I guess.
Well, n is fixed. You get now on input 1 to the n, so n is fixed. Could be even or odd.
And then we have to take n. Then we have to take n as input. So
N is not an input. I mean, the inputs are bit strings of length n. And we have many. We have 2 to the n possible inputs. We can query f on any of them, or polynomially many of them.
then we have to generate some inputs of length n. So
You just pick one uniformly at random, or what are you?
yeah, we can pick them at random, but we have to save them somehow. So
Yeah.
later.
Just 1 or 2 or 3 or 5 or?
Okay, let's go for 2 or so.
Okay, let's do input. On input x1, x2, both say uniformly at random from 0, 1 to the n. Yeah?
Yes.
Okay, good. Let's do that. And then,
We call it function.
yeah, okay, we obtain y1, so this is the image of x of f on x1, and y2 is the image of f on x2, yeah?
Yeah.
And then
In the next step, we can just XOR y1 and y2.
bitwise? Because y1 and y2 have length n.
Yeah, bitwise.
Okay. Okay, let's do that. So set, I set zi, say, to be y1i XOR y2i. So I is the XOR of the ith bit in y1 and y2.
Yes.
Yeah. Then
I think the result should be 0 on each zi, but
in which case? I mean,
if it's generated by fk.
yeah, but I mean, now you have to do something. You have to output a bit, sort of 0 or 1, and it should output 1. In your case, as I understood you, more often or with more with higher probability if it's a pseudo-random function.
If all the zi are equal to 0,
Output.
we output 1.
Okay. Okay. Mm-hmm. Okay, good. Maybe it works. I'm not sure. Yeah?
Can't we simple for 0 to the n? Because if it's fk, then it's always 0.
Let's do that later on, maybe. So actually, I think it goes into the right direction. I'm not sure whether it works. Now, what can we say about this probability for this algorithm? What's the probability that if D gets access to a random function, this algorithm outputs 1? That's something that we can analyze. Yeah?
I think 2 times 1 over 2 to the power of n.
2 times 1 over 2 to the power of n. Why?
Because the only cases where z is 0 and the function returns, or the d returns 1 is if, we do that both times. So there are just 2 cases. They both must be all ones, or they both must be all zeros, right?
No.
But if one is 1 and the other is 0 at one position, they would have
Yeah.
be 1 at this position.
Yeah, that means they have to be the same at all positions.
Yes, at all positions they must be the same.
Okay.
No.
But you said that you must be at all positions either 0 or 1.
Yes, no.
This here is the probability that this is true. This is the probability that y1 is equal to y2, right? Yeah? Which is, for a truly random function, what is this probability? For a truly random function, we pick y1. Well, assume that, okay, it's a little bit more complicated. Okay, I would like to write here it's 1 over 2 to the n, because we pick y1, y2 uniformly at random. Okay? And the probability that 2 bit strings picked uniformly at random, 2 bit strings of length n picked uniformly at random are the same as 1 over 2 to the n. The answer is not quite correct. Why? In this case, for this algorithm. It's a subtlety. x1, x2 may be the same, in which case y1 and y2 will be identical, because I pick a function. So anyway, and that's why your answer with 2 times was almost correct. But it's only almost correct. But anyway, it's roughly of this size here. Right? But then we have to analyze what the probability that we get a 1 here in this other case, where we picked something of this form here. I'd rather not analyze this online, I think. Because I think this is quite complicated to do. But I think your idea was kind of correct that, this is a linear function, sort of. It's a linear function in if I fix k, then it's a linear function. And this should... Yeah, but I'm not sure. But this wasn't a good exercise. But it gets into the right direction. I mean, this is, you want to exploit the structure, and this is linear. Right? If I XOR 2 x's, then the y's are XORed. Okay. So that gives you a strong hint that this is really cannot be pseudorandom. A random function will not be linear. Okay. But what you said is a much easier test of something, if something is linear or not. So you wanted to do what again? Okay. Okay, on input. Okay. On input 1 to the n, query f0 to the n to obtain y. Okay. Now what is the second step? Yeah.
If it's 0, we ask 1 and 0
Otherwise output. Okay. Yeah. Good. We have to analyze these two probabilities, right? The probability is over the choice of this key k or the function f and the internal randomness of d. But d has no internal randomness here. It's a deterministic function. Right? So we just have to analyze the probability of outputting 1 over the random choice of f or k. Okay? So what is the probability over the choice of f from func n that d f1 to the n is 1? What is this? Yeah?
1 over 2 to the n.
Yeah. Now we pick a function uniformly at random. The probability that it outputs 0 as the image of 0 to the n, this is, if you go back, special case of here, s is equal to 1. And x is equal to 0 to the n. So that's 1 over 2 to the n. Now we need to analyze this for our function family. And what is this in this case? If we have a function of this type and we query it on 0 to the n, what's the probability of getting 0 to the n? Yeah? Yeah. This is linear. Right? And since it's a linear function, the origin always gets mapped to the origin. So it's like you were in the right direction with the linearity, but this is much easier to do. In your case, what you should have done is, if you how do you check linearity? Pick pick 2 elements, compute the function value of one of the other, pick the function value of the XOR of the two, and compare that to the function value of the XOR. Right? If that was a right? Okay, and you see that this is not negligible, right? So your idea was, how do I check whether a function is linear or not? The way to do that is pick x1, or in this case x1, x2, compute f of x1, which is y1, say, compute f of x2, which is y2, and compute f of x1 XOR x2, which is y3. And then check that y3 is y1 XOR y2. That would be, like, this is obviously the test whether something is linear or not, right? Pick it, try it at 2 random points. Okay? And that's what you try to do. But then for a random function, well, you can easily check that. Then you would get to the same result, by the way. Because this is a completely new element, unless x2 is 0 or something like that. And then you would just get, well, this happens with roughly probably 1 over 2 to the n. Because y3 is independent of from y1, y2, except if this XOR is one of the 2 elements. Again, because then. Okay, but doing it on 0 is sort of the easier test. Okay, so, but what we can say here is, well, this is not, it's a pseudo-random function. Okay? But what I want to stress with this example is, we get oracle access to some function f. Not, you cannot distinguish, well, if k is this or that. You just get oracle access to a function. And then the function, the algorithm has to behave differently depending on whether the function was random or from fk. Good. So now I want to tell you that it's even more surprising that pseudorandom functions exist than that pseudorandom generators exist. So remember, if we have a pseudorandom generator, that was, say we have G, which goes from 0, 1 to the n to 0, 1 to the 2n, okay? And remember we had at this picture where I said, look, this is 0, 1 to the 2n. But the pseudorandom bit string, so the G of 0, 1 to the n, this is of size at most 2 to the n, right? So this is a tiny little blob in here. Right? The size of the two things is roughly 2 to the n, 2 to the minus n, the ratio between the two things, right? Now let's look at the pseudorandom function case. Here we have on the one hand func n, which we know has size 2 to the n times 2 to the n. Right? And on the other hand, if we look at such a keyed function, how many fk's do we have? So if we have f so we get either one element from this set or we pick something like this, and then we pick a function from this thing here, right? And this is, how many are there functions in this set here? Well, for each key there is at most one. There is one, but they need not even all be different. Right? Could be that for two keys, so this is here, so for two keys they could even be the same. Right? So this is at most 2 to the n. Right? So here our ratio between the pseudorandom strings and the two random strings is 1 over 2 to the n, in this particular case, right, where the pseudorandom generator is of length of expansion 2n. Here, what we get is 2 to the n divided by 2 to the n times 2 to the n. You see, this is 1 over 2 to the n minus 1 times 2 to the n. So this ratio is single exponentially small in n. This one is double exponentially small in n. So here and then within this you took, again, just a tiny little bit of this. So it's even more surprising that these things should exist, because they form such a tiny little part of the whole thing that how should you not be able to distinguish whether you get something from the huge thing or from this really, really, really tiny little thing. Okay? Okay. And then there are two surprising facts. These things, under certain assumptions, do exist. And without any assumptions, if you give me something of this type, I can construct something of this type. If pseudorandom generators exist, then pseudorandom functions exist as well. So we don't need stronger assumptions for that. How that's done, maybe if time permits at some point I'll give you a few hints, but it's an old construction from the 1980s that gives us this result. Okay? Okay. So far? Good. So here you can see this schematic view of a distinguisher. You live in two worlds, right? The distinguisher either lives in the world where here is a function, func n, and he has oracle access to it, or he lives in this world. Right? You cannot tell in which world you live. Or you behave similarly in both worlds. It's either on this side or this side, and it behaves on both sides. It behaves almost the same. That's the idea behind the construction. Okay, now what can we do with pseudo-random functions? How can we construct encryption schemes from it? That have a chance to be CPA secure. And remember, we know CPA secure encryption schemes must have probabilistic encryptions. Otherwise, it's gone. Okay? And so here is, and I often call this like the mother of all encryption schemes. This is really, from the syntax, this is what we basically do in encryption schemes plus something else. Okay, so assume we have a keyed, efficient, and length-preserving function, and then we define the fixed-length encryption scheme. So again, we first start by having a fixed-length encryption scheme. So for a key of specific length, it only can encrypt messages of a specific length. In this case, the length of the key and the length of the messages that we can encrypt are the same. And so we have a fixed length encryption scheme with message length n. The key generation algorithm on input 1 to the n chooses a key uniformly at random from 0, 1 to the n. Remember, it's an efficient length-preserving function. So all the input parameters, L key, L in, L out, are all the same. Now comes the important part, the encryption. How is it done? On input a key k from 0, 1 to the n, and a message m from 0, 1 to the n. It's a fixed length encryption scheme. We choose an R uniformly at random from 0, 1 to the n. That's the probabilistic part in the encryption scheme. And output the ciphertext. It consists of two parts. The first is R itself, and the second one is mx or fk of R. We apply our function fk, specified by this key k, on R, which gives us something of length n, because it's a length-preserving function. We XOR it bitwise with m. So our encryption, our ciphertext has two components, R, and the second component, mx or fk of R. How do we decrypt? Decrypt gets as input a key and a ciphertext. A ciphertext always consists of two components. And we know that they have, if the key is of length n, these two components must be of length n as well. And what we do, oops, yeah, no, it's a correct. So and then we output m as s, the second component, XORed with fk applied to the first component. Right? And this is obviously a correct encryption scheme, right? Because XOR, you do it twice. If you first encrypt and then decrypt, you XOR fk of R to m twice. XORing the same bit string twice is XORing 0. XORing 0 doesn't do anything. Okay? Yeah? So, and this is how we always, so modern cryptography, how we build encryption schemes is this here, this XOR, it's like in the one-time pad. It's again a similar thing to the one-time pad, right? We hide this message by some string here or by some operation. And because I make this randomized, probabilistic, I give you a hint. This error gives you information how I am hiding this M. Okay? But the important point is that the hint, the information that I give you, must be useless unless you know the key. Right? Because if it's good enough to unhide, unmask the message without using the key, it cannot be secure. Right? Okay. So I use this R and I use it to mask it, but I modify it by using the pseudorandom function. Yeah? And then obviously, if I have the key, I can use the hint.
So in that case, FK can't be linear, right? In a previous example.
Well, this is going to be the thing. If it's pseudorandom, then it's secure. If it's not pseudorandom, it's not secure. And nothing that's linear is pseudorandom. Exactly. That was kind of what I wanted to convey with my example. If you have something that's not, it's linear, no. I mean, linearity is something that you can easily check. All these things, if it has some property that you can easily check, forget it. It's not pseudorandom. Yeah? But if it's pseudorandom, then it works. And I will give you the intuition of the proof, give you before the break, and it's 2 sentences. Go back to what I said when we talked about eavesdropping secure encryption schemes with pseudorandom generators. If I do something with pseudorandom stuff, look at what happens when I do it with the truly random stuff. If that turns out to be secure, then the pseudorandom stuff should also be secure because pseudorandom and random are indistinguishable. If there is a difference between the 2 scenarios, the thing cannot be pseudorandom. Okay? So then, what happens in this construction is Fk, if this Fk is replaced by a truly random function. Yeah? We get a ciphertext, yes, correct, but not precise enough.
The second part is truly random.
Not precise enough. The first part is truly random. It's always truly random. The second part then is truly random and independent of the first part. You get what you said, it's really a truly random ciphertext. Yeah, the first and the second part both are truly random and independent, so that the whole thing is just a random bit string, which doesn't tell you anything about a message, right? That's the proof. Well, up to some minor things. Okay, yeah?
The ciphertext here is of length 2n, right?
That's something that I wanted to say. This is why this is not used in this form. The ciphertext is twice as long as the message. That's not good. That's not something that you want to do in practice. You don't want to encrypt gigabytes by twice as many gigabits or gigabytes, right? But one thing is clear. Actually, you can prove it. If you want to have CPA security, ciphertext must be at least a little bit longer than messages. You need probabilistic encryption, and because you need probabilistic encryption, you have to give the decryptor that's in possession of the key some information about the randomness that you used. Otherwise, he will not be able to do that. Here, I give it a lot, right? I give it the complete randomness that that's usually typically what you do, the complete randomness, but you do it differently. And we'll see later in today, we look at the so-called counter mode, where this is much better. And the counter mode is actually a very important technique that we use. But this is also like this kind of stuff. Get some randomness, use that randomness to mask the message, but in such a way that you cannot exploit the randomness unless you know the key. And then you do additional stuff to get even better security properties or more functionality. Okay? But keep this idea about the proof in mind. Replace this by randomness. True randomness should be okay. But also keep in mind that we are talking about this scenario here. You can ask for encryptions of your choice. So maybe you can exploit those to get some information about the randomness. So you have to exclude that case. But you will see in the proof that's really what we do. I will replace in the proof basically the true pseudorandom functions by a random function. And then I will also argue, yes, you're right, it's truly random. But I must take care that I don't give away information by these additional encryption queries that the adversary is allowed to make. Or I have to bound the information that I give away doing that stuff. Yeah? But that we'll do after the break. And we take a 15-minute break until 9:40, and then we do the proof. Oh, okay, good. So here is, so we do our usual proof technique, right? So let A be an arbitrary, fixed but arbitrary, sorry, other way around. Be a fixed but arbitrary adversary against pi f in CPA game. I'll just write this. Need to analyze its success probability. Need to analyze CPA advantage of, how do I usually do that? I usually forget my notation. Yeah. Need to define the CPA advantage. Here it is. Of A pi f of n. Okay? And we don't have multiple encryption, we have just the simple one, okay? Which is defined as this thing here, right? Private key CPA A pi f of n. I forgot the probability again. Is 1 minus 1/2. As usual, I'll ignore the absolute values. To do so, from A construct distinguisher D against F. Okay? Because our assumption is that F is a pseudorandom function. So we'll do that. Okay, so how can we do that? This is very similar to what we did in our proof for the pseudorandom generator construction, but with modifications because we have a distinguisher, so that has oracle access and not using the string itself. But otherwise, it's kind of straightforward. So as usual, a distinguisher gets as input 1 to the n, and it has oracle access to the function, and then we have to analyze what's the probability outputting 1 if f is truly random or whether it's pseudorandom. Okay. So we simulate a to the a with input 1 to the n. Okay, when a asks for an encryption of a message M, of a plain text, we are in the CPA game, right? So A is allowed to do that. We answer as follows. We choose R uniformly at random and query F to obtain F of R, and then output R, M, X, or F of R. So we use just our function F in our encryption scheme, right? Okay, so if that is pseudorandom, it's exactly our encryption scheme. If it's truly random, we replace it by a truly random function. And when A has chosen two messages M0, M1 from 0, 1 to the n, we choose bit, the challenger D chooses bit B01, and it chooses R01 uniformly at random. It queries F to obtain F of R, and again, it also encrypts the message, the challenge message with F of R, with the function F. And so all these encryptions are done with this function, okay? Consistently with this function. Simulate, and then simulate further, we simulate A with the input 1 to the n, and C, that's here, to obtain a bit B prime, and during simulation, the adversary can again ask for encryptions of his choice. We do this as here. And eventually, it outputs a bit B prime. And if bit is equal to B prime, then output 1. Otherwise, we output 0. Okay? Okay, so the first thing that we need to notice is if A is a PPT, then D is a PPT. Easy, okay? So A PPT follows D is PPT. Well, it doesn't do much except query and XOR stuff. And simulate A, obviously. But now we need to relate the advantage, this advantage, to the distinguishing advantage. Because we know that the distinguishing advantage of D is negligible, because we know that F is a pseudorandom function. So if we can relate them in such a way that if the distinguishing advantage of D is negligible, then also this CPA advantage is negligible, we are done. So that's our goal. And to do that, I just make what I said before, our break, formal. So we have this one. In one case, if F here is a pseudorandom from F, then we are really looking at the game against the CPA game against our encryption scheme. Right? That's exactly what we do. All the encryptions are done as in the CPA encryption scheme. If we use the truly random function, what we do is we actually play the CPA game against a random function. And I call this the conceptual scheme. Right? It's a encryption scheme. It's not really an encryption scheme because it's not efficient, but as we only use it as a conceptual, as a thought experiment, and not as something that we implement. So the conceptual scheme is pi prime, gen prime, eng prime, dec prime, gen prime on input 1 to the n. It chooses the f uniformly addendum von func n. So the key is really a complete function. It's not efficient. We cannot do that. It's exponentially large, but never mind. It's just a thought experiment. And output it as a key. Eng prime on input the key f and the message m. It outputs the ciphertext r, m, x, or this truly random function. Exactly what I said. And the decryption accordingly. So then what can we say? So it's not an encryption scheme since it's not efficient, but we can define this probability here. What's the probability of winning the CPA game against it? Because in a probabilistic polynomial time adversary never gets to see a key anyway. It's just up to the challenger. And the challenger can do whatever it likes. So we can define this here. What's in the CPA game, what's its advantage? Now we have two claims that will be enough to finish the proof. The first claim is very similar to what we did when we analyzed our pseudorandom generator construction, namely the distinguishing advantage of D as defined above is exactly the difference between these two things here. The probability of outputting 1 here and the probability of outputting 1 against pi f in the CPA game and the probability of outputting 1 in the CPA game against pi prime. Okay. And that follows because this is exactly this, and this is exactly this. And there's not much to prove there. That's actually the way I defined the distinguisher, right? The probability that it outputs in this case is exactly the output that it wins in the CPA game, by definition. Here it is. And if I use a truly random function, then I'm against the conceptual scheme. Huh? Okay. So now, the other part now that's again similar to what we did in our pseudorandom generator construction, I have to analyze this thing here. This here is something I want to bound, right? Now I analyze this here. This was in the pseudorandom generator case was the scheme pi prime was a one-time pad, where we knew that the advantage of any algorithm against the one-time pad in the eavesdropping game was 1/2. So now you may hope that here we also get a 1/2. Almost true, but not quite true. And the difference is because we are talking about the CPA game. There is additional information. It's not just 1/2, but what we can show is that the CPA advantage of IA against pi prime for every PBT, so this is this here minus 1/2, is not 0 as in the one-time pad and eavesdropping, but it's bounded by Qn divided by 2 to the n, where Qn is an upper bound on the number of queries, encryption queries that A makes. Okay? But now an important is A is a PPT, so the number of encryption queries is bounded by a polynomial. So this is bounded polynomial divided by 2 to the n. Polynomial divided by exponential is negligible. So this is negligible. But it's not 0. Okay? And so the core of the proof is this here. But let me just show that, before I do that, show you that claim 1 and claim 2 really give us the result that we want, namely that this thing here, minus 1/2, is negligible. It's just triangle inequality, basically. But So. So using two claims, we get this CPA advantage of A against pi f, then, which is the probability of winning the CPA game against pi f minus 1/2. This is the probability of the private key encryption CPA A pi f of n is 1 minus am I doing this correctly? Minus the probability plus. Just let me make sure that I don't write anything stupid in here. See, it's easy. That's what am I doing? Sorry. Yeah, okay, sure. Yeah. So this is private key encryption, A against pi prime, plus the same term, minus 1/2. Okay. In absolute values, this is upper bounded by, I take this and this. I know you don't like this, but I do this anyway. I make here less than or equal to triangle inequality. Yeah? This here is our distinguishing advantage, as we know, by claim 1. This is negligible. In fact, it's a distinguishing advantage here. So it's really this thing here. It's a distinguishing advantage. Advantage of D against F of n, which is negligible by assumption. And this thing here is by claim 2 less than Q of n divided by 2 to the n, which is also negligible. Okay. So the whole thing is negligible because it's upper bounded by the sum of two negligible things. Hence must be negligible itself. So it really comes down to proving these two claims. Yeah? Okay, so it remains to prove this claim 2 and to see why we have this Q of n in there. Or with this not, why it's not 0. Even against the conceptual scheme, you can win. And the reason you can win, you can look at this game here. CPA game, where is it? Where's my CPA game? There it is. If in our encryption scheme with these R, in encrypting this message here, we use the same R that's either used here, somewhere here, or here, then we win. Because then we know what f of r is, and we can just decrypt. Yeah? So if the randomness turns out in one of these queries is the same that you use in the encryption for the challenge message, for the challenge ciphertext for computation, then you are, no matter what f is, doesn't matter, because you get it. So we have to argue that this probability is small, that if the event does not happen, then we are in business. Then the advantage really is 0. And that is really what we do. So we really look now at this game here with the conceptual scheme. Yeah? Okay. So we need to prove this claim too. And so M0, M1 output of A in this step. Let me go back to this formal definition of step 2. Denote R0 is the randomness used by C, by the challenger in step 3. That is, C, let's call CB or C is R0 MB XOR F of R0. Yeah? Yep. And by R1 up to RQ of n denote the randomness used in answering the encryption queries. Okay. So similarly, the ith encryption query is computed as Ri, comma, and then Mi XOR this F of Ri. And now define the following event. Repeat. Is the event that there exists an I such that Ri is equal to R0. notice that in each encryption, the R is picked uniformly at random. Huh? No matter what you did before. You don't want to keep track of which randomness you used in your encryptions because you may do tons of them. Okay? Yeah? So, and then we have, let's see, the probability of repeat, which is the probability of there exists an I is equal to R0. This is upper bounded by the sum I from 1 to Q of n, the probability that Ri is R0. Huh? You just split it. This is just the disjoint sub-events, right? It's even an equality in this case. Now, the probability that Ri is equal to R0, in our encryption scheme, each time we pick R uniformly at random. So the probability that two elements picked uniformly at random from 0, 1 to the n are identical, which, as we already saw before the break, is 1 over 2 to the n. So this here is Q of n divided by 2 to the n. Okay? Yeah?
But what about if some Ri is equal to R1 or R2?
Doesn't matter. I don't care.
Okay.
That's irrelevant for me. Because I'm only interested in whether the RIs help you to decrypt this ciphertext. And if then the sum Ri is equal to Rj, I don't care because the randomness that I use in my ciphertext is R0, as you will see. It just doesn't matter. Okay? So we have repeat and we are done. Good. Now, okay. Let's see what we can do with this repeat event. This is actually one of the important techniques in analyzing these things. You identify an event that causes trouble. Condition on this event and see what the probability of this event happened is. And that helps you in analyzing the thing that you want to analyze, as we will see in the next few lines of the proof. Recall, we want to analyze the CPA advantage of A against pi prime. So in particular, we want to analyze this probability that it outputs 1 again in this scheme. Okay? Now I partition this event into disjoint sub-events. This repeat event, as I said, if repeat happens, the A will win. So I should condition on that. And if it's not happening, it cannot win, except with probability 1/2. So, and then we can, this is the probability of this thing. Is 1 and repeat plus the probability of this thing to happen, A pi prime n is 1, and this is a 1, and not repeat. Okay? definition of conditional probabilities. Yep. Just applying conditional probabilities. Now I do the following. I will do this on the board. I'll give you time to copy this. I need colors, but I don't have colors. Do I have colors in here? No. No colors. Right. Okay, so what I can do now is ignore this term, ignore this term. These things are probabilities. They are positive, but small, at most 1. So, but I replace this term by 1, right? And I replace this term by 1. So I make it all only larger. This step here is something that you see in many papers, and they don't explain it to you. And I remember that when I first encountered this, I spent hours before I understood what they are doing, and it's nothing. It's really just this. Okay? Now this here we know. We just analyzed it. Okay? Okay? Now what happens if there is a not repeat? If there is a not repeat, what we get here is R0 MB XOR F of R0. But we have never seen R0 before. So this here is uniformly at random independent of B. So what A gets here in this step is independent of B. All the other information that he gets, because the Ri's are all different from R0, they are all independent from B. Going back to our lemma about these truly random functions. So he doesn't get any information about B. So what he gets here is independent, stochastically independent from B, which means this is 1/2. In this case, we really are back in the business as in the pseudorandom generator case. Nothing, no information is given to A about B. Okay? Which implies that, so this here is bounded by 1/2 plus this Q of n divided by 2 to the n. Yeah, so then we are really done with our claim 2, right? Because the distinguishing advantage is just the whole, this here minus 1/2. It's this 1/2 that disappears. And we are done. And see, this is really a very intuitive proof. You see exactly what I'm doing. This repeat event is not some arbitrary event, but really the one thing where I capture what kind of information I get with my encryption queries. Right? In this particular case, for this particular encryption scheme. And I really follow this intuition that I just, instead of analyzing this pseudo-random scheme, I just analyze the truly random scheme and relate that with the distinguisher using that. Well, they cannot. They are almost the same here. And this thing here doesn't have any significant advantage. And I'm done. Good. So in the lecture notes, I wrote a little bit more about this, but this is here. Okay. Okay. Yep. Good. Okay. Now, if we look at this thing here, the construction here, it's a fixed length encryption scheme. The keys and the messages are of the same length. This is, yeah, it's CPA secure, but otherwise, because of this restriction, it's as useless as the one-time pad. Okay, but yeah, that's not such a big deal because we know that we have, by theorem 3.3, we have that it also has automatically multiple indistinguishable encryptions. So if you want to use it to encrypt longer messages, you can use the ECB mode, which simply says to encrypt a longer message, partition the message into chunks of length n. At the end, add zeros or something like that, I don't care, so that it really is a multiple of n. And then encrypt the whole thing by encrypting each chunk individually. Yeah? And that is still a good scheme, because this is what multiple encryptions are for. If the original one is CPA secure, then this one is also CPA secure, because we just do this encryptions now as a vector of encryptions. And multiple encryption says vectors of encryption are secure, are indistinguishable. Yeah? Good. End of story? Not quite. Because as you said before the break, in our encryption scheme, each message is encrypted using, each message of length n is encrypted by using an encryption ciphertext of length 2n. If I do this electronic codebook mode with our scheme, each thing is individually encrypted with a new random string, length 2n, or 2 times the original length of the message. Really bad. The length is bad, and also you need tons of randomness, which is hard to get by. Okay, so we would rather have a different scheme. And if you had a course on introduction to crypto or so, you have heard about other schemes, CBC mode and stuff like that. But what we want to analyze here and define and analyze here is a much nicer scheme, which is called the so-called randomized counter mode, which also circumvents this problem of encrypting a message by ciphertext that's twice as long. And so this is the second really important part. The scheme that I described, although not used with the pseudo-random functions necessarily, but things that we think are good, this hiding and using randomness, that's one thing that's always used in practice. And the randomized counter mode is probably today the most popular mode to get from fixed length encryption to arbitrary length encryption. So here's the ECB mode, pictorially, right? Now really specified to my construction pi f. Right? These are the message blocks. L of n, this is n in our case, but never mind. This, what I do now, can be done with any fixed length thing. So you pick R1, you push it into Fk, you XOR it within, you get C1, and then you do the same thing with R2, new one, and so on. And then your ciphertext is all the Ris and all the Cis. The randomized counter mode does the following. I pick one counter, okay, which is an element of 0, 1 to the n, say. That is my C0, the counter. Now, this is actually an n. So all these, but never, yeah, let's say it's n. Then I do an addition. What do I mean by adding 1 to the counter? Interpret the counter as a binary representation of an integer. Add 1 modulo n, modulo 2 to modulo n, yeah, or 2 modulo n, yeah. So that you get again modulo 2 to the n, sorry, modulo 2 to the n, so that this is again can be represented as a bit string. And then you use this counter plus 1 in Fk and do this. You do the counter plus 2 in here, do this. Do the counter and so on and so on. And then your ciphertext consists just of the counter and the CIs. Because that's good enough to decrypt if you have the key, right? Because you have the counter, you can compute counter plus 1, you can compute counter plus 2, and so on. And you can do all these things in reverse. Okay? And that's a much better, in terms of length, much better, because now my overhead, comparing length of ciphertext and message, is just this thing here. And if this t is large, I don't care. Right? It's a tiny fraction. So I have to add something. So typically, the counter would be of length 256 bit. And your message is megabytes. Who cares for 256 additional bits? Right? Okay. Yeah? Okay. Good. So this is the formal description of it. What we do here. Here I said interpreting is of length, assuming of length of multiple of n. And then the nice theorem is that if f is a pseudorandom function, then this new construction is secure. CPA secure. Let me give you the intuitive idea of the proof. You should know what I do. What am I going to do for the intuition? Yeah.
Making a reduction again to the case where we only have one encryption.
No, I don't do that. It's actually a good idea. Sometimes you do that. But here I'm just talking about the intuition. Why should that be secure if f is a pseudo-random function? Because it's secure if f is a random function. If it's a random function, new value, no relation between new value, function value, something uniformly independently of random of everything before, and so on. Then this here just makes sure that I do evaluate the function at different points. So the function values are independent of each other. So what I XOR here onto these messages is independent from each other. And then in some sense, yeah, I do think, okay, then it's like in the like more or less like the ECB mode almost. It's like ECB, should be secure. And that's actually the proof. I'm not going to the details of this proof, but I want to make, the details are in the lecture notes. I want to make just one thing clear. What we do here is, again, we define this conceptual scheme. We replace this by the truly random function. We get the same from adversary to distinguisher as I had before, with the modifications necessary because I use a different encryption scheme, the counter mode. But you can see that, again, I get this oracle access. I use this function for which I have oracle access to do the encryptions. It's exactly as before. I have my claim 3, which is as before. Yeah? And I have my claim 4, which is as before, except I have a different numerator here. Instead of Qn, where Q is the number of queries, I have Qn, 2 times Qn squared. And Qn is chosen in such a way that we have at most Qn encryption queries, and each has at most consists of blocks of at most Qn blocks. Okay. Yeah. So and then And then what we have to analyze again is, well, some randomness may get repeated. Some randomness that I use here in the encryption of my challenge ciphertext may have appeared here. Okay? But I use sort of more randomness. Even if here I use this counter, and if this counter here that I use here appeared somewhere here as a counter plus j, not just as the same counter that I started with here, but somewhere in between, then I cannot win. Then I will win, right? Okay? So I must guarantee that this counter is different from all these things that appeared in here. Not just the starting one, but everything in between, basically. Okay? And that's the reason why I have here a larger term. Because there's just more possibilities to get like this repeat or this collision. But that's it. That's the only difference. You have to analyze a little bit carefully, but that's it. The rest of the proof, identical. And the important thing, obviously, Q is a polynomial, Q squared is a polynomial, times 2 is a polynomial, divided by exponential, negligible. I'm done. Okay. So it's a good exercise to look at this proof, see, okay, it's roughly the same, it's just these technicalities that in analyzing this thing here is different. Okay. And this theorem is really the justification for the randomized counter mode in practice. And it's used all over the place. Sometimes CBC is used, but recommended typically is something that comes from the randomized counter mode. Okay, good. So that's the important thing to take away from this part here. CPA security as the next step towards really good security definitions. This construction, probabilistic encryption, this mother of all encryption schemes, randomness, hide the randomness sort of, or use the randomness, but in such a way that it's not usable by somebody who doesn't know the secret key. And you do not MB X or R, which we did in the one-time pad, but we pick R and then we modify it by FK of R. And this FK is something that you cannot kind of recover unless you know K. So it's again like a one-time pad, but not using the randomness directly, but taking the randomness, modifying it. But to be able to decrypt also give you the randomness. But because you modified it in such a way, you cannot. And nobody without the key, and somebody without a key cannot decrypt it. Okay. Good. But chosen plaintext security is not good enough, as it turns out. There are scenarios where people can actually not just get encryptions of plaintext of their choice, they can also get decryption of ciphertext of their choice. And then they want to decrypt some other ciphertext. This seems to be like weird. How could you do that? Get a decryption. Why should that be useful for? And how would you construct such ciphertext? Turns out that already in 1998 there was an important attack by Daniel Bleichenbacher using exactly this type of attack, and it attacked a standard, PKCS number 1 version 1.5, which was at that point standardized. It's RSA based, and it was even thought to be proven to be chosen ciphertext secure. Even so, chosen ciphertext security was already around. This was thought to be chosen ciphertext secure. Daniel Bleichenbacher attacked practical schemes online. So he really broke schemes that used this standard by asking servers to decrypt certain messages. The servers would actually answer, they didn't give him the complete ciphertext, the complete message back. But what you do here and in many other things is ciphertext must have a certain form, like beginning with a certain number of zeros, then 2 ones, and then something else comes. And what he did, he just sent over their ciphertext, and what he got back as answers was, no, this is not a valid ciphertext. This is a valid ciphertext. This is not a valid ciphertext. This is a valid ciphertext. And he used those things to do a binary search on the key, and was able to, with a few hundred thousands of these encryptions, decryptions, he was able to recover the key. So there were two things. First of all, this was the first real practical attack using these decryptions. The second was there obviously was a flaw in the proof of security for these things here. Turned out there wasn't really a flaw in there. People were able to fix it, had to modify the scheme a little bit, but then now there is a PKCS. I don't know what the current things are, but now it seems to be correct. But what he said, people did not learn the complete decryptions, but they got partial information. We don't want, in cryptography, we don't want to specify what partial information is or something like, okay, let's make sure that it's secure even if you get complete descriptions. Okay, so what I now want to do is I want to give you at least the definition of CCA security. I cannot, then we'll switch to something called message authentication, and which is interesting in its own right because it provides authenticity, one of the major goals of cryptography. But then we'll see that by combining CPA secure encryption schemes and message authentication codes, we'll get something that's CCA secure. Yeah? So we'll have to wait a little bit and first provide another ingredient, and then we can do the CCA security. Yeah? So here is our chosen ciphertext game. So we use the same, obviously the same strategy to define this chosen ciphertext security as we did before. We first define a game and then do the usual stuff. So here is a game. The chosen ciphertext game for encryption scheme pi between a challenger C and an adversary A. On common input N, C chooses the key. Then A asks for encryptions and decryptions of adaptively chosen plaintext and ciphertext. So you can ask for plaintext, please encrypt. Here's the ciphertext, please decrypt. Sometimes the answer for decryption will be not valid. And if you have that ciphertext have a certain format. Okay, and then eventually A outputs as before, two messages of the same length. The indistinguishability part is as before. So C chooses a bit B uniform dependent, computes the ciphertext as encryption of MB, and sends C to A. A asks for more encryptions and decryptions, but at the end, he has to guess which of the two he has to determine which of the two messages was encrypted. Obviously, if I now allow him to ask for the decryption of C, he will win. So I forbid that. But that's the only thing that I forbid. So he can ask for any encryptions that he likes of any plaintext as before, M0, M1, I don't care. But at this point here, he is no longer allowed to ask for the decryption of C. At the end, he has to output a bit B, and then we do as before. Okay? But here, he is allowed to ask for any other decryption. He may modify C a little bit, flip a bit, multiply by 2 or do whatever. That's already legitimate. That's allowed. Okay? So that's the power of this thing. Even by you can ask for modifications, but not just for this one thing, not. Okay? And then we do the usual thing, right? It's as before, the decryption queries. We have this game here, the visualization as before. And then we have, obviously, again, the CPA advantage as the difference in winning, probability of winning minus 1/2 in absolute value. And we say that the scheme is CCA secure or has indistinguishable encryption on the chosen ciphertext attacks if for every PPT adversary there's a negligible function such that the CCA advantage is negligible. Okay. Yeah. So we abstract from all possible adversaries and that they maybe get only partial information about decryptions. We just say you get them, period. Make things as strong as possible. Forbid the just one thing that makes the definition vacuous. Observation, CCA security obviously implies CPA security. Well, encryption queries are still allowed. So any adversary against CPA security is also an adversary against CCA security. So if CCA security, I have CCA security, then I also have CPA security. But not vice versa. And in fact, the scheme that we had, and that's a good thing, if you remember our ciphertext that we had in our mother of all encryption schemes. Well, how would you be able to attack this scheme with a CCA attacker, one that can actually ask for decryptions? Don't try plain text queries or some encryption queries, just one decryption query is enough to break the scheme.
We can give the same R, right? We can give, like, supply the same R with the ciphertext.
Yep. For example, you can pick C prime to be R, and then you put in here anything you want. Say S prime. Huh? So why does this work now? Yeah.
We could use 0 to again.
Yeah. Now, this is my decryption query, right? I get an answer back M prime. Now, why? That's good enough to break the scheme. Why? Yeah.
Because we can just take this thing from above and here we have the FK of R in it. So we have to XOR it.
Which one? Yeah, you have FK of R for this R here. How?
So M prime is equal to the second part of the ciphertext XOR XOR FK R.
Here it is. I XOR it to this one, see what I get, M0 or M1. I'm done. You wanted something slightly simpler, just do here X or like a 1 in the last component or something. But keep this. That's the right idea that you had. You ask for a ciphertext where you keep this component here. Because that's the thing that you want. And that will give you information about this here that enables you to get the MB back. Right? So that's why you both had the same idea. It's important that you keep here the same R in here. Otherwise, you get information that's probably useless. Okay, good. So keep that also in mind. CCA security is not implied by CPA security. Keep in mind the mother of all encryption schemes. And as I say, always keep this in mind. If you have a construction with something that's pseudorandom, security is shown usually by going from pseudorandom to truly random, analyzing this thing. Remember this thing with the repeat event. We have certain events that cause trouble. Condition on these things. And then you analyze with this conditioning and analyze the event itself and so on. Okay. We probably, for that, we have another exercise maybe that gives you an important little lemma in cryptography called the difference lemma. That is very useful. And I used it today, basically. Okay, good. That's it for today. See you next week again. Thank you.